Okay, we can start. Thank you everyone for joining. So today we have Olivier Absil from the University of Liège. He's a very well-known astronomer in Belgium, I should say. So he obtained his master degree at the University of Liège also, and also he continued to do then his PhD, which he divided between Liège and Paris. Afterwards, he went to do several postdocs, both in Liège and at the University of Grenoble. And then he came back to Liège, and if I'm not mistaken, since 2013, you have a fixed position. And his expertise, as you can see, is exoplanet imaging, and that will be his talk of today. So please, Olivier, you have the floor.
Thanks a lot. Very happy to be here. So in the next 50 minutes or so, I'm going to try to convince you that machine learning and deep learning in particular has a significant role to play in the future of exoplanet imaging. And so I cannot resist by starting my talk with this very nice video montage, which shows 12 years of monitoring of the most emblematic planetary system that has been detected by direct imaging so far, which is called HR 8799. And so what I want you to take out of this very nice video is the quantity of information that we can get out of direct imaging observations. So this planetary system is composed of 4 giant planets on orbits that are typically beyond the orbit of Neptune in our solar system. So these are giant planets that are very far away from their stars. So the first thing we know from this is that with direct imaging we can probe the outer parts of planetary systems, which are usually not accessible to indirect detection methods like radial velocities or transits. So a second thing that we can do, of course, when you look at this movie is that, you can witness the movement of the planets, and you can constrain the architecture of the planetary system by just looking at the motion of the planets over time. And that gives you clues about how they form, how they evolve, and that's even more important if you can tie this back to the formation of the planetary system. So if you can look at these planets when they are young enough, when they are still interacting with their birth environment, so the disk of gas and dust in which they were formed, then you are really able to constrain the methods, the ways these planetary systems have been formed. So here, in this case, I'm just showing an example of a planetary system of 2 planets that were detected in a young circumstellar disk. Finally, last but not least, having direct image of these planets allow you to separate the photons from the planets from those from the stars. And once you do that, you can present these photons on the entrance of a spectrograph. And that means that you can now study the composition of these planets and try to understand exactly what they are made of, how the atmosphere looks like, and also tie that back to the whole story of their formation. So the problem with direct imaging is that it's really a formidable challenge. So you can compare that to trying to observe a small firefly right next to a bright lighthouse that would be several hundreds miles away. And of course, you need to find a way to fight this huge contrast between the star and the planet, or in this case, the lighthouse and the firefly, if you want to make a detection. And so for that, we have a series of tools, which are either hardware or more software. So on the left-hand side, I show 2 main hardware tools, which are adaptive optics and chronography. And on the right-hand side, the more software tools, which are related to the observation strategies and the image processing. And the name of the game will be to try to find this needle in the haystack and try to find whether this little dot here is really a planet among these sea of speckles that you typically get when you observe bright stars with large ground-based telescopes. So as I said, 2 main hardware tools. So just to give you a very short overview of what this consists of. So adaptive optics are now equipping most of the large ground-based telescopes. And the idea is to measure in real time the shape of the wavefront that was distorted by atmospheric turbulence, and to correct it in real time in order to make the wavefront as flat as possible, so that most of the light is concentrated back into what you expect to be the response of your telescope to a point-like source. Once this is done, you can put this starlight onto what we call a chronograph, whose purpose is to try to divert the stellar light or to block it in some way, so that in your final camera, in your focal plane, you are able to make a high contrast detection of the planets without being annoyed by this very bright star in the middle. So now there are a couple of tools that are more like software tools, which consist in trying to find a way to distinguish between things that are real, that are around your star, and things that are due to your instruments not behaving perfectly. And so the way we usually do that is to leverage the fact that the sky is rotating above us, while the detector will be tied to the telescope and the instrument, and all the aberrations that are linked to the telescope and the instrument will be fixed on the detector, while you can let the sky rotate above you. And so if you can make short exposures of the sky as it's rotating above you, what you can do is the following. You can get a series of images over time where you are pointing the star in the middle so that stays fixed, but all the objects around the star are rotating as the sky is rotating above you in a fully deterministic way. So once you do that, and if you take this series of images and you just take the median of these images, you can try to capture all the things that are kind of fixed on your detector, all the things that are linked to your telescope not behaving properly, your instrument not being perfect. You can try to capture that with the median and subtract it from all the images in your stack of images. Once you do that, you can get rid of a lot of the residual starlight in your images, and you get a new series of images where the dynamic range is now much better because you have already subtracted most of the remaining stellar light. Of course, I mean, in here, you have already used your adaptive optics, your chronograph, so already you have canceled part of the starlight, but not all of it. Once you do that, you just derotate all the images to align them to the same position, because you just know how the sky is rotating. This is purely deterministic, and then you just stack them together in order to increase the signal of your planet as much as possible. And this is how we do exoplanet detection in most of the cases. So this is just a video to show how it looks like. So these are like almost raw data, so just stacked for like 20 seconds, where you see that indeed there are things that are kind of fixed. So you see that all this diffraction pattern that is linked to the shape of the telescope pupil is constant. You see that there are a lot of speckle patterns that are flickering because of atmospheric turbulence, but that you see there is an underlying structure that is kind of fixed. So now if you take the median of that stack of images, and you already see that in this raw data, because this planetary system is pretty bright, you already see that there are things moving around, and these are the planets that you are looking for. But in most cases, you don't see them in raw data. So if you remove the image from all the images, the median image from all the images one by one, this is what you get. And so this is the same movie played with the same, at the same speed, where now you see that after removing the median, you are seeing the planets much clearer. And you see that, for instance, here, there is another one that shows up that was completely overwhelmed by the stellar signal in the first stack of images. And finally, if you co-add and if you derotate and co-add these images over time, this is what is shown here. So as you stack more and more of them, you see that not only you are getting more and more signal from planets, but also you decrease even more the amount of speckle noise that you get from the star. Just because of the derotation and mean combination, you get another level of starlight suppression. And so this is how these planetary systems have been detected so far. The problem is that, as I said, this technique is still very complicated and relatively young. And to date, there are only a few tens of these planets that have been directly detected. And so this diagram shows all the planets that have been detected up to like last year as a function of the semi-major axis and the mass of these planets. And the filled dots show all the planets that have spectroscopic measurements, so from which the light was presented to a spectrograph to try to determine the composition. And so you see that in blue here, I mean, first you realize that indeed we probe the other part of planetary system that are really not accessible to other methods, but you also see that there are still only a few of these planets that have been detected. And they all are like struggling between the brown dwarf and planetary regime, which is typically divided at 13 Jupiter masses, where deuterium burning is supposed to start happening in the cores of these objects. So now it would be, of course, very interesting to have more of these planets because we want to know more about them, we want to know more about their formation, about their composition, and so for that we have to increase the sample of planets that we have access to. And this summarizes the situation. So all these red arrows here, they represent one realization of a planetary population predicted by formation models. And the shaded blue region here shows the region to which we are sensitive in terms of direct imaging. So this means that we are at this point of time only like scraping the top of the iceberg of the planetary population. And if we want to start investigating all these planets that are supposed to be formed in this region here between typically 1 and 5 AU, which corresponds to the snow lines in their birth environment, we need to go deeper and fainter. And so to go deeper and fainter, there are a couple of ways. You can either improve your hardware or you can improve your software. The main way to improve the hardware is just to build bigger telescopes. And that's what Europe is going to do with the ELT. The United States is also working on this kind of extreme large telescopes, but the subject of the talk today will be about software improvement. And so I'm going to be asking myself, how can machine learning help in this endeavor of trying to go fainter and deeper? And I'm going to be talking about two things. The first one is about how to improve the performance of the hardware that we have built. And the second thing is how to improve the software performance of image processing. Okay, so let's start with the first point. And to understand the idea behind the first point, we have to try to identify the things that are limiting the performance of the current instruments. And it is widely recognized that one of the things that is limiting the performance of the current instrument is what we refer to as non-common path aberrations. And so these aberrations are due to the fact that when your adaptive optics systems is working, it's measuring the shape of the wavefront at a position that does not correspond to the position where you put your chronograph. So there is a lot of optics in between the place where you separate the beam between the adaptive optics module here and the position where the detection is done. And all these optics can have their own aberrations, and these aberrations will not be seen by the adaptive optics system, will not be corrected, and will thus impact the measurement here and create these long-lived structures in your images that are the one that you are really that you really want to suppress. So if you want to make a better job, you need to find a way to measure the wavefront at the place where it matters. So this is the general scheme of a chronograph with the light coming from the telescope, going through some aperture here. A part of the wavefront is sampled here and sent to the adaptive optics system, and then you enter your instrument where you can place some optics in order to like massage the photons and create the low brightness region that you want to use to make planet detection. And so there are several ways of doing chronography. One of them is to put an opaque mask in the focal plane. And in this case, you could think, well, I could use a light that is reflected back by this focal plane device and use it to make a measurement of what the wavefront looks like at this position. You could also say, well, there are some chronographs that send the light outside of the image of the pupil of the telescope in a downstream pupil plane. You could also use that light in order to send it back also to a camera and try to use that information to retrieve the shape of the wavefront and correct it in real time. But what I'm going to be talking about today is a way where we don't add any additional hardware to the instrument. So we just assume that the instrument has been built and that we want to make the best use of it. And so for that, what we can access is just what we observe on the scientific camera. And so now the name of the game will be to try to infer the shape of the wavefront based on this information that we get when we do our science measurement. And this is called focal plane wavefront sensing. So we try to use the information that we have in the focal plane in order to sense the wavefront and to feed it back to our control system. So the main problem with focal plane wavefront sensing is that in the focal plane of the telescope, what you do with your camera is to measure the intensity of the light. You don't measure the phase. And because you lose this information on the phase, there is a non-unique solution to your wavefront sensing problem, which means that based on one measurement of a point mass function, like this one, there is an ambiguity on which of these two wavefronts was producing this specific PSF. So there is a non-unique solution to your reconstruction problem, which means that if you don't have additional information, it's impossible for you to know which correction you should send to your deformer mirror, which you should send this one or that one. And another way to see this problem is shown on the top right, where you see that if you send a sinusoid ripple onto your deformer mirror, you create two speckles that are conjugated, and these speckles will remain the same if you shift your sinusoid by just half a wave. So in order to solve this problem, you need additional information, and typically this is something that is known for a long time in optics. You can recover enough information by adding a second image to your reconstruction algorithm, and if this image is taken out of focus, then you lift up the ambiguities on the shape of the wavefront that was at the origin of this specific PSF. The problem is that usually you don't want to do that, because if you do that, that means that half of the time you will measure defocused PSF that will not be useful for your science. So there are other ways you can try to lift up this ambiguity. I'm just going to show two of them here. So one of them is to add some asymmetry in the pupil of your telescope. Well, you can do that inside the telescope, or you can do that inside the instrument. If you make this pupil asymmetric, you can show that this lifts up the ambiguity on the reconstruction of the wavefront. Another way that we are investigating right now in my group is to use a vortex chronograph. And the vortex chronograph is a phase mask that is put in the focal plane that creates like a helical phase ramp on the light of the star. That's the reason why it's doing the chronographic effect. But if you have two different signs for this helical phase ramp, one positive, one negative, then you can show that you can also induce enough diversity for you to be able to reconstruct the wavefront. So now that we have found a way to lift this ambiguity, now we can use a machine learning framework in order to recover the wavefront. So the reason why we want to use machine learning for this is twofold. The first one is that the relationship between what you measure in the focal plane, be it with phase diversity or with the vortex chronograph or with asymmetric pupil, that doesn't matter. What you measure in the focal plane is linked to the pupil plane in a nonlinear way. Just because you are making intensity measurements, you measure the square of the electric field, this is already a source of nonlinearity. And deep neural networks are very good at capturing this kind of nonlinearity. The second thing is that the classical methods to recover the shape of the wavefront from the PSF measurement are iterative methods. And so these iterative methods prevent you typically from doing real-time control because they take time to converge. So with a deep neural network, you should be able to address both challenges of first solving this nonlinear problem, and second, to be able to make inference in real time. And so this is what we have started to do in my group. So there are other groups that are also looking at these issues, but I'm just going to present you what we have been doing. So the idea to solve this problem with a neural network is to try to train the neural network to associate the measured PSF with the input phase that were used to produce them. And so typically what you want to do is to create a labeled data set, a training data set from simulations where you have injected a known level of aberrations. So typically when you draw from a random distribution of wavefront errors, you separate them into a series of modes. So here I'm separating them into Zernike modes, which are an orthogonal basis to describe aberrations on a circular pupil. And so these Zernike modes are drawn randomly, and they correspond to a phase map that is shown here. So these are your labels. Whether you use the Zernike coefficient or the phase map, it doesn't matter. It's just you know what you have injected into your simulator, and then you propagate that to through a model of your coronal graph, and then you get the PSF. So in this case, I'm showing the in focus and out of focus, but it would be the same with the asymmetric pupil or with the vortex diversity. Well, typically, you want to do some kind of pre-processing in order to increase or reduce dynamic range in your images. Typically, you will use some kind of square root stretching or something like that in order for you to see better the details around the bright center. But so now you are you have access to a series of images that you will use for training, and each of them will be associated with a label, which is the phase errors that were used to produce these images. So once you have this training data, then you can use a neural network architecture that you will train to match the inputs to the outputs. So your PSFs to the labels that you have, be it the Zernike coefficients or the phase maps. Here I'm showing the phase maps. And so with these kind of deep neural networks, well, I'm not going to go into the details, but the idea is that they are doing some convolution operations which are which preserve some of the properties of the images and try to compress the information in the image until you reach this bottleneck, and then decompress to reach the phase map that you want to predict. So what you will then do is to try to update the parameters of your deep neural network. So there can be millions of parameters in this deep neural network by comparing the output of the network with the labels that you had pre-computed. And so you define a loss function, and you try to optimize this loss function by using some gradient descent techniques, which are very classical, with the help of the fact that these kind of network, they are differentiable. So you can use backpropagation to conserve all the gradients in your network that will speed up the optimization of the loss function quite a bit. Okay, so now we have trained our network, and now we can try to use the network to do inference. So we show the network unseen PSFs, and we try to reconstruct the phase that were used to produce them. And this is the result we got. So in black, you see the input. So this is as a function of the Zernike mode, I mean all the Zernike coefficients. And this shows the amount of aberration that we injected into all of these Zernike coefficients. You see that if we are just using the in-focus image, where we know that there's some ambiguity, there are some modes we can predict, but there are also some modes where we have absolutely no prediction power. So these are even modes that will create the same PSF if you use one sign or the other for them. Now, if you use only the out-of-focus images, or even better, the in-focus and out-of-focus images, then you can retrieve all the modes, and you can make a very good job measuring the aberration in each of these modes. So you see that in this case here, we injected about 350 nanometers RMS into the whole wavefront, and we are left with only about 5 nanometers in each of the modes after the reconstruction. So the question we are asking ourselves now is whether this is good enough. Is the network doing a good job reproducing these aberrations? And the answer is yes, because actually we have shown that these networks, they can basically reach the fundamental limit, which is just limited by the photon noise in the images. So, well, basically the black dashed line here shows the fundamental limit as a function of the brightness of the star. So here less photon, here more photons. So the more photons you have, the better the prediction of the wavefront should be able to do. And this is exactly what we see. So depending on how much aberrations we put at the start and the exact training conditions, we might not exactly reach the photon noise limit, especially here when there is a lot of information in your image because your star is very bright. You will need to train even more for the blue dots to get back down to the theoretical limit. But in principle, we are there. Another important question is whether the network can generalize, which means whether the network can predict things that it hasn't seen before. Especially if you train your network in a small aberration regime, can it still predict the aberrations if they are much larger, or the other way around? If you train your network with large aberrations, can it predict small aberrations? And these curves, they show the result of this study here, where you see, I mean, with the orange curve, that when you train at low aberrations, it's hard for the network to do proper predictions at high aberration, but the other way around is not true. If you train a network at high aberration, which is shown with the blue curve here, even at small aberrations, you can still make a reasonable job predicting the aberrations. And so typically what we will do is to show the network a relatively wide range of aberrations so that it can make predictions for a wide range of input aberrations. So what I've shown so far is just based on simulations. And actually, we have also shown that this works well with in-lab data. So we can produce in-lab data where we just use a deformer mirror to produce some aberrations inside the instrument. And we acquire a lot of these data. And we use that as our training data set because we know exactly how much aberration we have put in our system. But once you go on Sky, this is not true anymore. Because when you observe on Sky, you not only have your instrument, but you also have the whole atmosphere that you have to take into account. And you don't know anymore what are the labels. You don't know the status of your system at a time. And so now the problem is, what do we do when we don't have any more labels? So we could think, well, we have trained our network. We could maybe apply it directly on Sky, but usually this will produce subpar results. And so one of the things that we are now investigating and developing is the following. So we are trying to use a method that is called unsupervised learning, which means that you don't have access to labels anymore, and you try to find another way to train your network. And the way we have proposed to do is the following. So once the network has predicted the Zernike coefficients, instead of comparing that to labels, what we do is that we repropagate through our simulator this Zernike coefficient to predict what the PSF should look like. And now, instead of comparing our extracted Zernike coefficients with our labels, we will look at the predicted PSFs and we will compare them to the measured PSFs. So that requires, of course, to have a simulator that is relatively realistic. But if you have a sufficiently realistic simulator, then you can use this kind of scheme on Sky directly. As you get data on Sky, you can just propagate that through your network, through a simulator, and then use that as your training data set by just trying to match the output of your variational autoencoder. So this is what it's called, or simulator-based autoencoder to the input that were used to feed it. And so you, even better, if your simulator is differentiable, then you can still use the same kind of technique, backpropagation through the whole stuff, through the simulator and through the network, in order to make a very fast training. So that's for the training, but of course, when you operate your system, you will stop at this place to do the inference, and you will just from the Zernike coefficient extract the correction that you need to apply to your deformed mirror. And so the first results of this study, they show that the two techniques, so the simple convolutional neural network and the simulator-based autoencoder, they produce almost the same kind of results. So here it's only for the very small aberration that there is some deviation, but globally we get the same kind of accuracy, which means that this other framework is also close to the photon noise limit in principle. So now that's where we are. So the next step for us will be to try that on Sky, and we have planned on doing that at Subaru Telescope. So that was for the first part. So now I want to say, to spend the next 20 minutes or so talking about how to improve the performance of image processing with neural networks. And for that, I want to come back to the principle of angular differential imaging. So as I explained to you, the idea is to take a stack of images over time where the planets and other things around the star are moving because of the sky rotation. Instead of using the median to subtract from each of the image of the stack of images, you can do a better job using more advanced technique, like, for instance, principal component analysis, which will basically project each of the images onto a low-rank subspace that is supposed to capture the things that are not moving or moving slowly in the image that are supposed to be associated with a star. And so by projecting each of these images onto the principal components, you try to make the best possible reconstruction of the PSF for each individual image. And so that's supposed to provide better correction than just median subtraction. Well, that's actually a first, if you will, way of using machine learning, because you can consider that PCA is some kind of machine learning technique, unsupervised, that is just learning from the data how the PSF of the star looks like in each individual image. Well, this technique has been used for 10 years or even more, and we are still struggling with this technique for some reasons. The main one being it's hard to tell what is real and what is fake in the final images. So for instance, if you get this image or that image as an output of your PCA processing, you would say, well, I've seen something that looks significant. I can measure the noise, I can measure the signal for that bright spot there. I can compare it to the noise in other apertures that are the same distance where the noise is supposed to behave in the same way. And you would say, well, I have detected something significant. The signal-to-noise ratio is above 5, I'm happy. But actually, this is not always the case. So here, this is just a bright speckle, and because there are so few samples, independent samples at very small separations, Gaussian statistics and your statistical tests just do not work anymore. So one of the challenges is to find a proper way to distinguish between things that are real and things that are still linked to residual starlight in your final images, especially if you work at very short angular separations, which is exactly the place where we want to be. So I remind you about the idea of going deeper and closer in, and it's for a good reason, because we want to probe these regions that are very close to the star. And so this is where, once again, machine learning can come to the rescue. But the problem here now is that we don't have any way of having labels anymore in our data. And even if we knew there was a planet, we don't even know enough planetary systems that we could use that as a training data set, because we know, like, as I said, a few tens of planetary systems. And even if we kind of gathered all the data that we have, it wouldn't be enough for you to train a deep neural network. So if you want to be able to train a neural network, you need to create synthetic data, labeled data that you will be able to use to feed the training of your neural network. And so here, the good thing about these kind of observations is that, I mean, you have your stack of images, but you also know what the image of the planet should look like. So you know the response of your system to a point source. And so you can inject these predefined image structure, which corresponds to the PSF of your telescope, inside the raw data to make as if a planet was present in your data. And so you can pass that through your processing algorithm and see whether you are able to recover it or not. Typically, this is what we do when we want to know the sensitivity of our algorithms to the presence of planets. But so now we can also use that to make like massive injections into our raw data at different positions with different brightnesses, and use that as our training data, because we have control upon what we inject in our data. Well, so it took a bit of time to figure out how to do that properly. At first, we thought, well, we would just inject stuff into the raw data, and we would just present the raw data to the machine learning algorithm and ask it to find out whether a planet was injected or not. But it didn't work out, just because there is such a high contrast between the star and the planet, even after adaptive optics and after chronography, that it was almost impossible for the machine learning algorithm to recognize what was signal from what was noise. On top of that, all the speckles in your image, they basically look like planets because they have the same size and they have brightnesses that can be of the same order as the planets that you want to look for. And so in order for the machine learning algorithm to be able to train, we had to use some tricks. And the trick that we have found is that before showing our data to the machine learning algorithm, we first do a first pass of PSF subtraction with PCA. So using this exact same technique that I showed here. So instead of working with these raw data sets, what we will do is to use these post-processed data in order to feed the machine learning algorithm. But now the problem is that instead of having like hundreds of frames in our raw data, we have only one frame. For one data set, we have one frame, one final frame, and that's not enough to train a machine learning model once again. So we are facing the same issue. Even if we could inject planets in all the possible pixels in our image, we would just end up with several thousands of frames that would not be enough to train the machine learning algorithm. And so for that, what we do is that we divide the post-processed image into little patches where we have injected the planets or not, and we use some kind of data augmentation techniques in order to mix up different kind of signals for the machine learning algorithm to see enough diversity in the training data. And so, well, typically, well, that's one thing. And the other thing is that because, as I said, planets look very much like speckles, even in the final image. What we do is that we also use the fact that when you reconstruct the PSF with the PCA here, you can use various number of principal components in this reconstruction. And depending on the number of principal components that are used, the signal and the noise will look slightly different. And so that's what I show here. So this is typically the result of injecting planets in our data and processing them through PCA with different number of principal components. And so you see that when we have injected something, the signal is preserved for many different number of principal components. While if you compare with the noise here, you see that the noise has a completely different behavior from the signal. Even though there are some cases where you see, well, there's something that looks more or less like a planet here. I mean, this is just a speckle, if you wish. This speckle will not stay as you change the number of principal components in your PCA subtraction. And so we can use the fact that the signal and the noise are behaving differently as a function of the number of principal components for the machine learning to pick up this behavior and be able to distinguish between the two kind of classes. So C- without injected companions and C+ with injected companions. Okay, so now, I mean, once again, once we have our training data, so we have all these series of patches where we have either injected or not a companion in it. We can use that to train a neural network. I will not go into the details of the training, but yeah, it seems to work. The training is working well, so we are happy. And I want to just take a little minute to introduce this very nice tool that is called the hype curve, that shows the expectations as a function of time. And we were here. That was the first time we used machine learning for high contrast imaging, and we were, I mean, quite confident that we could go up this curve and be able to get good results. And indeed, applying this neural network to actual data I mean, it was producing quite nice results. So this is the same HR8799 system. This is, I mean, of course, this is pretty obvious detection. With PCA, you see that the planets are showing up very nicely. If you compute the SNR from this image, you see that, I mean, the SNR is high. And it's no wonder that our network, which is called SODIN, is picking them up nicely. So that's not enough to see that it's working. Well, of course it's working, but is it working better than PCA? And the first test that we did seemed to show that this is the case. So this is the result of injecting many fake companions after the training, so at places where they were not injected during the training, and trying to see if we can pick them up. And this tells you the fraction of companions that were retrieved. So this is the true positive rate, so it goes from 0 to 100%, as a function of the number of false positives that we got in our image at the end of the day. And so we injected relatively faint companions that were just barely detectable with PCA. And so you see that our network SODIN seemed to provide a much higher true positive rate while keeping the number of false positives to a very small number. And so we were very excited to see that. And that's where we reached the peak of inflated expectations in our hype curve. And as you can imagine, then we have to write down. Because a couple of years later was introduced the Exoplanet Imaging Data Challenge, which is a community-wide initiative in order that aims to compare the performance of different image processing algorithms for high contrast imaging. And so there are a series of standardized data sets that are where fake planets have been injected. And so we were quite concerned to see that at the end of this experiment, we saw that our networks, like SODIN or another one, were at the bottom of the ranking because there were just way too many false positives. And this is one of the results where there were like 5 planets that were injected that were properly recovered by the network, but you see that there is a lot of crap around and things that are above our detection threshold. And so, yeah, of course, we were pretty concerned about that, and this is where we reached the trough of disillusionment. But, yeah, we thought there was still some future in this method, and so in the last couple of years, we have been trying to include some of the lessons learned from this data challenge into a new version of our network. And there are 2 main things that we have included. I will not go into too many details here, but one of the lessons learned is that having an algorithm that works locally, that can adapt to the local noise behavior, was an asset. And so we tried to find a way to divide the field of view into different regions where the noise had different properties. Typically, at the center of the image, you are still very much dominated by the speckles, and so the speckles have a non-Gaussian statistics, and you want to train your machine learning model to be able to properly take into account this non-Gaussian noise here. While if you are looking for stuff further away, you are generally more limited by background noise, which is Gaussian, and where you want to train another type of model. So I think I will skip the details on how we managed to divide the field of view, because it's just too technical. And I just want to also introduce a second thing that we have added to the network. So if you remember these classes that I've shown, you saw that the signal and the noise were behaving differently. And so you can use that as a morphological information, but you can also use that in a slightly different way. And you can form these kind of curves, which tell you the signal-to-noise ratio of your little patch as a function of the number of principal components. And so you see that there is a different behavior between pure noise, which is scattered around 0, and when you inject a fake companion, you have this kind of peak, where there is a competition between the amount of noise that you remove as a function of the components. The more components, the more noise you remove. But also, if you use more components, you start eating out some of the planetary signal, and so at some point, this curve flattens out and starts to decrease because you start removing planetary signal from your data. And so what we have done is to use these 2 tricks. So first one, to divide the field of view into 2 parts, so speckle regime and background regime. And the second thing is that we have injected this kind of curves inside the final layer of our neural network. So when the planet is present, it looks like this. When it's absent, it looks like that, and that gives another lever to the machine learning algorithm to distinguish between the two categories. And this is where we are now. So this was the result of the data challenge 3 years ago. This is our new entry to the data challenge, and so you see that now the updated results are very good. So we are still very close to the top of the ranking for the true positives. That was already the case before, but now we have found a way to control the amount of false negatives, so fake detections, false positives in the detection. So we have been slowly climbing up the slope of enlightenment, and now we are finally reaching this plateau of productivity. So hopefully we will have some nice results to show in the future. Okay, I'm starting to run out of time, but I still want to say just a few words about a last thing that we have been doing over the last few years, another way of using machine learning. So I've explained how we can use machine learning to improve the operations of the instrument, how we can use machine learning to improve the processing of the data, but I'm just going to take like 5 minutes to briefly introduce another way we can use machine learning, and that's the idea is to use machine learning now to make the best use of the final data sets. So we have our science-ready data, which is typically for direct imaging the spectrum that we collect for the planet. And usually the way these spectra are used is either to compare them to grids of models or to use a more fancy technique, which is atmospheric retrieval, where basically what you use is that you are using Bayesian sampling methods in order to compare the observations with your model, and that you loop and you update the parameters of the model until you find something that looks more closely to the observations. And by using this in a Bayesian framework, you are able to derive posteriors, which basically tell you the probability of the parameters of the model given the data. So these methods are now very much used in exoplanet science, be it for transit observations or for direct imaging observations. But the problem is that these techniques, they have limitations. I would say two main limitations that we could address with machine learning. One of them is that in order for this process to converge, you have to make many calls to a relatively complex simulator. So this simulator is basically producing spectra as a function of parameters, and this can be quite complex. So that means that it takes a lot of time for these sampling methods to converge. The second thing is that they are usually not very good at handling very high dimensional parameter spaces. So if you want to use a lot of parameters in your model, these techniques start to, they do not scale well with the dimensions of your problem. And so now there are ways we can replace this Bayesian sampling methods with machine learning methods, and there were some that were proposed in the literature of the last couple of years or so. So you could try to train a neural network to retrieve the model parameters. So you could teach the network to recognize pairs of spectra and parameters. But we want to do that a little bit better and stay within a Bayesian framework, because, well, most of these machine learning methods, they have some drawbacks. Like, for instance, if they are instantaneous, usually they do not produce a very accurate posterior, or if they still produce an accurate posterior, then the speed improvement is not great. And so over the last couple of years, we have been using a families of technique that is called simulation-based inference that poses the problem within a proper Bayesian framework. And, well, I don't think I will have time to enter into the details, but the idea is to train a neural network to produce not only predictions of the parameters, but produce predictions of the posteriors. And you can do that using specific kind of networks, which are called transformers, which basically transform an input distribution into something more complex, and you can train your network to match by drawing from your prior to match that with a posterior. So the advantages of this kind of simulation-based inference techniques is that, I mean, they check all boxes. So they provide accurate posteriors, they don't compromise onto the accuracy. They are fast, so that means that you train your network a priori, and once it's trained, the inference is just like a simple pass through the network, which can take typically a few seconds. So that means it's also scalable to complex models. So you pay the upfront price of training the model, but when it's done, you have that available to you. And finally, it's also testable. I will briefly come back on that. I just want to show some nice results here, just to show that we have been able to reproduce and even improve upon the results that have been obtained with the Bayesian sampling methods. So in orange, these are the results for nested sampling, and in blue, these are the results of our simulation-based inference method, which is called neural posterior estimation. And so instead of spending like 100 of hours doing the retrieval with multinest, we now pay like 17 hours to generate all the data for the training, like 13 hours using GPU acceleration for the training, and then the inference only takes a few seconds. And one of the good things with this kind of techniques, once the inference is very fast, you can start doing tests about the quality of your retrieval. So of course you can make posterior predictive checks. That's something that you could also do with MCMC or nested sampling. But you can also build this kind of curves, which are called coverage curves. And these coverage curves, they basically tell you about the truthfulness of your retrieval. The idea is that you draw from the prior, you draw many synthetic observations, you retrieve from them, and you look at where the ground truth is placed on your posterior. And you count how many times they are within a given credibility interval. And so if like 50% of the time you are within this 50% credibility interval, that means that your retrieval is well calibrated. And so you want to reach this diagonal, which tells you that your retrieval is well calibrated, and it's something that you can only do if the inference is very fast. Because you can, with MCMC, you would need to do, I mean, every point on this curve which would require 130 hours to compute. So it's impossible to make sure of the truthfulness of MCMC or nested sampling. Well, you can do that with this kind of techniques. Okay, and I'm coming to the end of my talk. So I hope I've been able to convince you that not only today high contrast imaging is becoming a mature technique, but that there is still a lot of room for improvement, and that machine learning is a technique, I mean, a series of techniques that then can really be used to fill that room for improvement in different ways. So either by improving the instrument operations, improving the image processing, or even making better use of the final data product. Thank you.
Fantastic talk. Thank you very much. Any questions or comments, feedback?
Yes, thank you for this very interesting talk. Now that we are still fresh in our minds, this neural posterior estimation, I wanted to, can you tell us a little bit more on how can you train those networks or these things? Because it sounds hard to do, no?
Okay. Well, I will not be capable of entering into the details of the training. But what I can tell you is that, so typically for these kind of retrievals where we have a parameter space that has like 20 dimensions, we can properly cover the parameter space by using typically a few millions of samples. And these, the way this network trains, so these transformer network trains, scales very nicely with the dimension of the parameter space. So, well, you know what is usually called the curse of dimensionality, which is one of the reasons why the MCMCs, they start crumbling when you have too many parameters. This seems to be much better handled by these methods. So, well, the idea is that you cover the parameter space, so you sample from your priors, and you assign labels. You form pairs of spectra and parameters of your model. So you create these pairs through your simulator, okay, and then the basic idea is to try to train like a classifier to recognize the pairs that are true pairs, so where you have the parameters and the associated spectrum, and you have created wrong pairs, where you have put like parameters that do not match the spectrum. And you try, and you basically train a kind of classifier to recognize things that are real, so real pairs of parameters and spectra with respect to fake pairs. I won't be able to say more because I'm just not an expert with these things, but this is what I understand from the training. Yeah, sure.
Thank you, Olivier, for the impressive talk. It's impressive to see all this progress on all these fronts, important front of direct imaging. Just one question about Skexeo. Can the CNN keep up with the frame rate of the system?
Yeah. So we have two different ways to approach the problem. So either we use the fact that Skexeo has focal plane cameras that can run at kilohertz frame rate, which means that turbulence is kind of frozen in the images. And in that case, indeed, we could run the CNN at kilohertz frame rates to try to reconstruct not only the non-compass aberration, but also the residuals of the atmospheric turbulence. So because we have like frozen things. And this could work with a pre-trained network because it doesn't matter for the network whether the aberrations come from the AO residuals or from the instrument itself. So that's one thing that we could do actually because the CNN is fast enough to do that. But the second thing and the thing that we are going to try to do is to train a network to recognize things that are moving fast, like the residual aberration from the AO, and things that are static or quasi-static, like the NCPAs. And so basically, we are going to present the network with like batches of 10 or 100 images over 10 or 100 milliseconds, and teach the network to recognize things that are moving and things that are fixed, so that it only corrects for the NCPAs. That's what we are planning to do.
Any more questions or comments?
So if I understood correctly, your system is working for a vortex coronagraph. Would that also work with vortex Nuller?
Okay, so you're talking about the wavefront sensing. All right, let me think. Definitely not out of the box. The problem with the vortex fiber Nuller is that we have only one output, or a couple of outputs, which are typically the fibers that are put in the focal plane of the telescope. We would probably need to have a series of fibers in order to control the wavefront properly. So I think this is probably possible, and actually seeing what the guys at Skexeo are doing with the glint experiment, using just a series of a few fibers to try to control the optical path difference between the different subpupil of glint. I think that gives me some hope that we could do the same kind of thing with the fiber Nuller, but we would need to reformulate the problem a little bit for it to match the output of the fibers to something that we can control, which would probably not be the full wavefront, but at least we could control something that I'm pretty sure of that.
Okay, thank you.
Thank you. I want to ask about the reasonable predictions this machinery can make. You showed this nice plot of semi-major axes and masses, and you want to go down to the left. How deep could you reasonably go? Could you find Earth mass planets at 5 AU with these techniques, or is that too optimistic?
Definitely not with the current generation of telescopes. But the hope is that these techniques will bring the additional delta that we need for the extreme large telescopes to reach the terrestrial planetary regime, which is really kind of borderline actually right now. There are some predictions that show that we could in principle reach that regime, but if we really go down basically to the photon noise. And this is, I think, where machine learning can help to go down the extra step to reach that photon noise limit.
But in principle, just simple PCA could also do that on extremely large telescopes.
Yeah, the thing is that we know that PCA is not, is not perfect. And when we see the post-process images obtained by PCA, there is still a lot of junk in there. And we know we don't really reach the photon noise limit, especially close to the star. There are still a lot of speckles remaining after the PCA processing. And this is where we think we can not only improve the image processing, but even more do a better job controlling the instrument so that these speckles are not present from the start.
Okay.
Any more questions?
Yeah, so maybe a comment first. You were saying that having more outputs at your vortex fiber nuller could help start provide that. There's a person that's been working on photonics lantern fed by vortex fiber nuller. So that could be maybe a way to obtain several outputs, and it could be, for example, a way to work with that. But I still also have a question. For the SODIN network, I didn't really understood how you made progress for like fixing the threshold, and in general, in this type of techniques, how do you go about picking a threshold, adjusting a threshold?
Well, I think you put your finger on still the most critical thing that has not been really addressed yet. At this point, the way we define the threshold is really based on trial and errors, actually. So we try to see where the division between the two populations of like fake things, noise and signal appears, and of course there is this gray region where we cannot really, that we cannot really access. So one of the keys to the improvement of SODIN is that we have been able to provide the machine learning algorithm with more information to distinguish between the two classes. So one of the challenges and one of the reasons why the first version of SODIN was having so many false positives is that there was some class overlap between the negative class and the positive class. So when you inject things that are sufficiently faint, you start having in your C+ class things that look like noise. And the network starts to pick up noise as being a true signal. And so it's really touchy to train in this regime where we are like really in between at the edge of the detectability. And this is where injecting these additional handcrafted features like the SNR curve or dividing the noise regimes has been kind of key. But we still, we are still struggling. I should really be honest about that. We are still struggling about how exactly we should define the threshold when we do the final detection.
Because indeed, those faint planets that are beyond your threshold will still exist in the final images. So, but I guess it's a matter of ambition. Do we try to reach for them and put them in the training set? Or?
Yeah, and there is the next step in this conundrum is that once you use true data and you claim a detection, and you are the only algorithm that can claim the detection, how are you sure that you are doing the right thing?
And that's why statistical inference has been preferred, because they can say, okay, under these hypotheses, I can be sure at this percent.
Yeah, definitely. This is something that is hard to control.
Okay, I would like to take the opportunity to ask the last question myself. So, could you go back to the first convolutional neural network that you showed, and where you talked about excess noise? Because it really confused me.
Oops. Is it this one?
No, go further again. Go further. Where you talked about the excess noise.
Which part was it? Was it about the wavefront sensing or the?
yeah, yes, I think so. Could you go a bit further?
Further.
Yes, yeah, so go back.
Oh, yeah.
This one really confuses me because it shows that it's easier for your network to succeed on low signal to noise images than it is to high signal to noise images. And you mentioned this, yeah, there is more information, but I don't understand that because the information that's the size of your very first image so that's the same in both cases. So why is it easier to handle crappy than to handle very nice images?
Yeah, well, it's because I mean, as you can see, the photon noise limit is at a much higher level of aberration, which also, I mean, you even see, well, maybe should I? So you see a strange behavior here actually at low flux, is that the network seems to be behaving better than the photon noise limit, and it's actually kind of regularized by the amount of aberration that you have put in the first place. So you see here, I mean, the horizontal line, they show the level of aberration that you have used to train the network. And at some point, the photon noise limit becomes even larger than this level of aberration that you have injected. And then the networks, they start to strangely behave even better than the photon noise limit because just they do not add any additional noise. They just say, I do not see anything, and the aberration that I get at the end are just what I've put in the input. So that's for this part. But so here for that part, the thing is that if you want, so because there are more and more photons, you are in principle able to detect smaller and smaller aberrations in your image. The thing is that if you want to detect these smaller and smaller things in terms of aberrations, that means you have to use more and more information in your focal plane, typically going further away from the star. And this is where, if you want to be able to capture this with your network, you need to have more and more data in order for it to be able to capture the behavior of the things that are further and further away, just because there is more information there, and if you want to capture it properly, you will need to train your network even more for it to be able to reproduce these kind of things.
Thank you. So I'm sure that you will be able to reach Olivier maybe to ask more questions. So let's thank Olivier again. Thank you very much.
Thank you. Sure, put it back there.